Hi, my name is Kanya. I'm going to give my presentation on network congestion and implementation of TCP congestion control algorithms. Coming to the introduction, TCP is one of the most important transport layer protocols in the computer networks. It provides reliable and connection-oriented communication between sender and the receiver. The TCP ensures that data is delivered in correct order without any errors and without any duplications. The problem facing in this network is when many users send data simultaneously at the same time, the network becomes overloaded. This condition is called network congestion. Network congestion leads to packet delay, packet loss, and reduced performance. Solution for this network congestion is the TCP uses congestion control algorithms to manage traffic. It automatically adjusts the sending rate based on network conditions. It also prevents network collapse and ensures stable communication. Here in my simulation, I've done to simulate congestion in a controlled network and observe how TCP reacts using its congestion control mechanisms and analyze performance changes during congestion. Objectives. Objective of my simulation is to create a network simulation that produces congestion conditions, to study how TCP handles packet loss and packet delay, to implement TCP congestion control mechanisms such as slow start, congestion avoidance, fast retransmit, and fast recovery, and to observe changes in performance metrics like throughput, packet loss, and delay, and finally to analyze how TCP adapts dynamically to the network congestion. What is network congestion? Network congestion occurs when the amount of data entering the network exceeds its available capacity, causing delays and packet loss. During this congestion, the routers become overloaded with incoming packets. Packets wait in a queue that's also called buffer for the processing. If buffer is full, packets are dropped. Transmission becomes slow and unreliable due to this. The causes of network congestion. The main cause of network congestion is the network congestion does not occur randomly. It happens due to several technical limitations and traffic conditions. First one is the high traffic load. In this, many devices send data simultaneously, and there is a sudden spike in network usage. The example of this high traffic load is video streaming, downloads, and online meetings. Second one is the limited bandwidth. In this, each link has a fixed capacity. When demand exceeds the bandwidth, the congestion occurs. Third one is the router buffer overflow. In this, the routers store packets in the buffer queues. If buffer becomes full, extra packets are dropped. Fourth one is busy traffic. Here, data is not always sent evenly. Sudden bursts of packets overload the network in this busy traffic. Next is inefficient routing or design. Here there is a poor network configuration in this, and there's a longer or congested paths increase load on routers in this inefficient routing or design. So even a small network can experience congestion if traffic exceeds the available resources. Effects of congestion. Effects of network congestion. There's an impact of congestion on network performance. That is, when congestion occurs, the entire network performance degrades significantly. There are several reasons. First one is the increased delay, that is latency. Packets spend more time waiting in router queues, and there's end-to-end communication becomes slow in this latency. Second one is packet loss. In packet loss, the router buffers gets full. Due to this, the excess or extra packets are dropped. This also leads to retransmissions. Next one is packet loss. Next one is increased retransmissions. Here, lost packets are resent by the TCP. This increases network load further. Next one is reduced throughput. In this, the less useful data is delivered per unit time, and overall efficiency decreases in this reduced throughput. Next is poor quality of service. Here the um, video or audio buffering issues occur, and there's a slow web page loading. The web page loading becomes very slow, and there are unstable connections. From this, we observe that the congestion creates a cycle, that is more traffic, more loss, more transmission, that leads to more congestion. Need for TCP congestion control. Why is congestion control necessary? Without congestion control, network performance can degrade rapidly, leading to congestion collapse where very little useful data reaches its destination and the remaining data uh, is sent back. The problems without congestion control leads to excessive packet loss, continuous retransmissions, network resources get wasted due to it, throughput drops drastically, and communication becomes very unstable. Benefits of TCP congestion control. Here, the benefits are: this prevents network collapse, improves bandwidth utilization, maintains fairness, wherein the only some amount of data is reached to a destination without the congestion control. Next one is enhances reliability, and it also adapts to different network conditions. Here, the TCP does not send at a fixed speed. It continuously monitors the network and adjusts its transmission rate to achieve high performance with minimal congestion. TCP congestion control. TCP uses a feedback-based congestion control mechanism to regulate the amount of data transmitted into the network. Instead of sending data at a constant rate, TCP continuously adjusts its transmission speed according to the different network conditions. Now, how the TCP detects congestion? TCP assumes congestion has occurred when packet loss is detected and timeout is occurred, and when multiple duplicate ACKs are received. Main TCP congestion control algorithms are slow start, congestion avoidance, fast retransmit, and fast recovery. In slow start, it rapidly increases transmission rate at the beginning, and in congestion avoidance, it increases transmission rate gradually. And in fast retransmit, it quickly retransmits the lost packets. And fast recovery, it recovers from the packet loss without restarting completely. The working principle of these TCP congestion control algorithms are the TCP follows the rule increase transmission rate when the network is free and reduce transmission rate when the congestion is detected. My simulation setup. Uh, um, There's a simulation environment. The network congestion scenario is implemented using a network simulation tool such as Cisco Packet Tracker. In the network topology, the simulation consists of a simple but effective topology. This is sender, which is PC1, router, the bottleneck node, the receiver, that is the destination node, also is that is presented as PC2, PC1 and PC2. Here the data flows from sender, then to router, then to receiver using the TCP protocol. Configuration details are of my simulation are: protocol used is the TCP, data type is continuous packet transmission, the bandwidth is limited on router link to create congestion, and the buffer size is restricted at router. Traffic load is increased intentionally to overload the network. Working of simulation. How the simulation works is: sender retransmits the TCP packets continuously, routers forwards the packets to receiver. When traffic exceeds capacity, the queue builds up at a router and packets are delayed or dropped then and there, and TCP detects this and activates the congestion control algorithms. My purpose of this simulation is to create a realistic congestion scenario to observe TCP behavior under heavy network load and to analyze packet loss, delay and retransmission. This acts as a control environment to study how TCP dynamically reacts to congestion in real world networks. Now I'll be showing you the simulation. I'm opening the Cisco packet tracker. Here I'm opening this. I've taken one router, two routers, two switches and 4 PCs. PC 0, IP, open the Cisco packet tracker for the simulation. I have for this simulation I have two routers, two switches and 4 PCs. I have switches of 2960 to 24TT switch and routers of 2911 and PCs PC0, PC1, PC2 and PC3. I have connected the PC0 and PC1 to switch 0 with using the copper straight through cable, and PC2 and PC3 to switch 1. This I have connected to switch 0 and this to switch 1 through the copper straight through cable. The same I've used the copper straight through cable for connecting switch 1 to router 1 and switch 0 to router 0, but for connecting router 1 to router 0 I've used the serial DC cable. I've given the IP address for each PC. Here 1, this is the IP address. Here desktop IP, this is the IP address. The router I've configured here. I've changed the serial. Now the same with I've done with the router 1 also, which I've done to the router 0. Here we've gained. Now we'll ping. Go to the command prompt. Ping 192.168.168.10.2. Here it's pinging. This is for PC0. Now we'll go to PC1 and give the address of PC0 while pinging 92.1.10.1. Same. Now, and in the edit filters, I've only selected ICMP and TCP. Others all I've disabled because we need only those two. Now we'll start the simulation. We'll also configure this ping 192.168.10.4. Same way for PC3. Command prompt ping 192.168.10.3. Yeah. Here showing, and here we can tell the type. This is ICMP. Here it's the destination. Once again check it, TCP and ICMP. Here it's showing. It's also showing the last previous device and the present device. We'll reset the simulation. It's already there. And we'll take it. See, it's given it's showing the reply time from 192. The time is 9 millisecond. TTL is 128. Bytes is 32. The second reply is from 5 milliseconds. So it's showing. Again, we'll do it. Ping 192.168.10.1. It will give it. on command prompt 192.18 point this is PC 0, so point 2, yeah, then PC 2 PC3 command prompt and again ping 192.168.10.3. Here it shows the previous events. Command prompt, this shows the previous events. Now I'll give it ping 192.168.3. Point 4. And now we'll start the simulation. CMP and TCP. Here it's showing, here the events are showing. This is the destination. Same as here, it reaches the destination. Now we can see here, we can go to command prompt and it shows the events. Reply from this IP address, the bytes is 32 and time is 4 milliseconds and TTL is 128. By this we can check all the other PCs reply also. The packet losses. The average time is 4 milliseconds for every PC. Here, see, bytes. Now coming to the presentation. So by this simulation, we know that it successfully simulated network congestion and I demonstrated the implementation of TCP congestion control algorithms in the network environment using the Cisco packet tracker. It shows how TCP intelligently adapts its transmission rate based on network conditions to maintain reliable communication and prevent congestion collapse. Thank you.